So, well, I'm Luis Garcia-Mozos, and I'm going to talk about my research project, which is the Back from Space project, BFS. It's a project done in collaboration with e.NOVA Space, and the target is to develop a reentry kit capable to retrieve payloads from space. And in particular, we're going to focus in the case of a 3D spacecraft from which we want to retrieve a 1U payload. In particular, the work is based in these 12 rigorous works that were defined by e.NOVA, which include several tasks like the system definition, reentry and trajectory aspects, aerothermal mechanisms, and other more system-related like cost and customers, etc. We have addressed more than or around half of them during the project, especially the more technical ones. And well, this is a bit of the state of the art of some other projects which use similar concepts to ours. These accelerators from deployable systems from NASA and inflatable systems from the FS2 program. And well, this has been a bit the timeline of the project. We started with a literature review, and then the first months during the second semester, we focused on the landing trajectory and landing accuracy definition and define a propulsion module and select some candidates. And now this year we started redefining a bit the trajectory and reiterating with that. And then we focus on the definition of a payload model for an in-orbit demonstration, in-orbit validation mission. And now this couple of last months, we did some thermal analysis and mechanical analysis for the structure of the heat shield. So main topic of the project was this trajectory and landing accuracy study. The scenario is to retrieve a 4.5 kilogram spacecraft from the ISS orbit, more or less, so we said 400 kilometers. Working sequence that we follow is first to find the best landing place to achieve and target it with a Keplerian trajectory. Then we took into account with the software the risks from KNS, the atmospheric effect, and reiterate a bit the trajectory to reach this position. And finally, we introduced some variations in the parameter to assess the effect of each of them that we have in the results. For that, for the Keplerian trajectory, we decision an elliptical trajectory to ground, actually a perigee of 75 kilometers, because the atmosphere will do the rest to get it to ground. And yeah, we decided to land on ground, not on the ocean, because it's easier to recovery. And for that, the best place to do it in the world was found to be Woomera Range Complex in Australia, because it's the largest place for this on ground, largest protected area with more than 600 kilometers in the diagonal. Although we have to take into account that the trajectory is not optimal because we are constrained to the ISS inclination, 51.2 degrees. And in this case, we see here the lines that it's not the best diagonal, but if we took the best case is around 470 kilometers, which is very, very good and more than anywhere else on the Earth. So first, we define this Keplerian trajectory. The calculations are developed mostly in the second semester and that report. But basically, it's implementing a MATLAB subroutine to make it more easy to iterate. The ISS orbital plane, then apogee at 400 kilometers, perigee 75 kilometers. Then argument of the perigee is defined by the latitude that we want to achieve, and the longitude is fixed by the time window. So we took all these parameters and simulated in the brisk with these parameters. Instead of using the compass geometry, we use an equivalent sphere of 4.5 kilograms and 50 centimeters of diameter. And we suppose ideal thermal properties to avoid ablation. And with this, we introduce these parameters, and the result we get, we see that the landing happens in the ocean, of course, way before than what we would like because of the effect of atmosphere. So we reiterate the parameters and find that the best way is to increase the argument of the perigee and then adjust the time window. And with that, we see that we achieve a landing in the middle of Woomera, more or less. So this is going to be the nominal case that we'll take now for introducing the variations in the parameters. So I was saying, this is the nominal trajectory, and we're gonna, from this case, we're gonna introduce variations in the parameters to get the effect of each of them. First, this is the ballistic coefficient, which is going to be a major driver of the accuracy, and in particular, not the ballistic coefficient that also takes into account the drag coefficient, but the ratio mass over mass that we're going to call the reduced ballistic coefficient. And apart from this one, we're also going to study the altitude of the perigee and the argument of the perigee. So for the CV ballistic coefficient, we introduce a range of masses for the spheres and diameters. This combine all of them between each other, getting around 100 cases of different values of the ballistic coefficient, and these are the results. All of them fall within the Gomera ranges. And what we do here is to plot the downrange against the ballistic coefficient and do a quadratic regression and get this analytical expression for small variations. Then same for the final velocity. We also see a quadratic shape. So it tends to be flatter for high values of the ballistic coefficient. Now we do the same for the altitude of the perigee, introduce increments of 0.5 kilometers and analyze different cases and see how's the tendency. In this case, we see that it's a linear tendency with the altitude of the perigee and the downrange, the distance from ground. And we see that this is a very delicate parameter because in the analytical expression, we see that 1 kilometer of change in this nominal altitude of the perigee would induce 100 kilometers of error on ground. We see that for the final velocity, there's no correlation. It's independent from that. Same study for the argument of the perigee. The more we increase it, it tends to fly longer, let's say. Again, we do this approximation, this linear progression again, and we get this expression with the argument of the perigee in decrease. It's important. And again, we see that the velocity is not affected by this. Then what we do now is to combine all these parameters together and do a sort of worst case scenario with 200 grams of mass of error, 3 centimeters in the diameter, 1 kilometer in the altitude of the perigee, and 0.5 degrees in the argument of the perigee. And we combine them in a way that all of them contribute to the same direction in the two cases, so more to the southeast and more to the northwest. And this is what we get, the two results that will fall almost in the front, in the border of the landing zone. So this is a good first approach to know the range of the order of magnitude of the values that we can afford. What we did now is to also combine the expressions that we presented before with the superposition principle, as this is for small variations, and validate the previous results. We see that the results are close to each other. They are not perfect because it's not really a small variation what we introduce here, but more of a worst case. But still, we see that the order of magnitude is good, so we can validate the expressions as a way to estimate the effects. Then what we did is to study how will be the repercussion of these requirements here on the requirement that we have to request to the subsystems, to the propulsion system in this case that will provide the orbit boost. Is related to the altitude of the perigee, and for the maximum distance that we have for Gomera in this diagonal, we see that 235 kilometers will be the worst error we can afford. We get this, we see, with only a 0.6 centimeters per second error in the delta V. So it is very sensitive, and we have to require the landing system, the propulsion system for the orbit borne accuracy of in the order of 0.1 meter per second. Then there's also the pointing during this boost that will have to be provided by an AOCS system. It will induce two errors. One is that the effective velocity will be less in the linear direction. It's related to the previous effect, and we see that for the case, we're going to focus on the case of a 5 degrees error in the pointing. It will induce a downrange error in the end of 123 kilometers, which is a lot, but still acceptable for the ranges that we were dealing with. And the other effect is the induction of a transversal component that will induce a slight change of plane, but we see that the velocity that we induce is very small. The change of plane of inclination is less than 0.1 degrees, so The downrange error in this transversal direction is only 15 kilometers, which is perfectly acceptable for Gomera. So between these two components, both cases were for 5 degrees, remember, so we say that pointing accuracy in order of 1 degree is acceptable. And that will be all for the trajectory definition. We move on to the definition of this payload module for in-orbit demonstration and validation. First thing we did is to define a set of preliminary requirements for the mission. We are gonna want to measure during the reentry. We're gonna wanna collect data for temperature, heat flux, pressure, accelerations, and then GPS, position and velocity, and transmit all this data to ground, fitting everything in a 1U format if it's possible, and having all the auxiliary means to manage the data handling and to have the necessary power supply. So what we did is to then define a design architecture and decide a set of hardware that could fulfill these requirements. Many of them were taken from flight heritage of EntrySat project, which is actually, it had a very similar mission to what we want, is to recover data during the reentry. So we have these temperature sensors, also selected some pressure sensors, this accelerometer, the IMU, antenna for the GPS that is actually going to be the same that we can use also same model for the Iridium, the GPS receiver, same antenna for the Iridium for the data transmission in this case, and the Iridium model. We also have to confirm, because it's possible that we can use the same model for GPS and for Iridium. In that case, it will be very important to save that space. Data handling is going to be managed by the onboard computer by ComSpace, and for compatibility with ComSpace, it's going to be good to use also from then the electrical power supply system. And after evaluation of the power budget, if we need it, it's also possible to use an additional module of batteries for the system. So this would be the architecture, and this would be an overall block diagram of the layout. Also important to highlight that we will probably need as well a sensors interface board to manage the analog sensor with the onboard computer. And well, and also this will be, we will have to take into account the interface with the rest of the platform and the other systems. Then we did a very rough preliminary check, getting the external dimensions of all the elements and trying to fit them in a 1U module, in a very rough CAD model. And we saw that everything would fit in first instance. We will also have to take into account now the interfaces, the space for the wires, cables, and so, but at least it looks like it's feasible in first approach. Then we move on to a thermal analysis, and for this, well, we're gonna study the effect of the thermal shield and how thick it should be. We're gonna start from a given input external temperature of the surface, and we're gonna have two objectives. First, we will have a layer of flexible thermal protection system, F-TPS, and we want to keep the internal temperature below 600 degrees, and then the payload that will be in the inside has to be insulated to keep it below 60 degrees. And for that, we will follow these steps. First, we will focus only on the thermal conduction through the thermal protection system, the external system. Then we will study a case of imagine that we don't insulate the payload, and we just assume that they are not in contact with the F-TPS and how the radiation transmission will be. See that we're going to need an insulation and size the insulation, the multi-layer insulation. And then we're going to validate this with a case, because in principle, we're going to use external temperature in a constant value, and then we will validate with a variable case. Geometry is this the flexible thermal protection system has a conical shape made of Nexen material. The payload is going to be modeled as a 10 by 10 plate, so the exposed surface of 200 grams made of aluminum, and it's going to be covered with a multi-layer insulator of this conductivity. And these are the different input temperatures that we're going to use from e.NOVA's BFS specifications. We have to withstand these two first criteria, so they're going to be actually the most important ones. 1500 degrees for 1 minute and 500 and 1000 degrees for 5 minutes. And we're also going to use these other cases for validation. So one for a longer time, averaging the mean temperature, so around 650 degrees for 700 seconds. And finally, this one with the variable profile with some margins. Then for conduction, the first step is to analyze the conduction through the external field. We start from Fourier's law. We also use the equilibrium of temperature, the evolution of the internal temperature T2, put them together, integrate, and get this analytical expression. That depends on the thickness of the flexible thermal protection system, which is the variable we're gonna size. And we studied this for the different scenarios, and we see that the second one, which is good because it's one of the requirements from e.NOVA. So we see that this is one of the most demanding scenarios. Is the most demanding one. We need a 3.6 millimeters layer, which is 2.85 kilogram, which is not few for the small that it is. But yeah, this will be the sizing. Then we are gonna keep the same thickness to now study with this internal temperature, how it will be transmitted through radiation to the payload, to a bare payload. In this case, we have to take into account the time variation, so we're gonna follow a more numerical approach. And this is the evolution. We see the green curve, which is the temperature of the payload, but for long times it tends to just follow the temperature of the F-TPS. So we see that it's not acceptable to have it without an insulation. And what we do here is to introduce a multi-layer installation and study this transmission of conduction through the multi-layer insulator. As the temperature of the internal F-TPS varies, it will induce a variation in the temperature of the MLI. And it would depend, the final temperature of the payload T4 would depend on the thickness of this MLI, which is, again, the parameter we want to size. And after some iterations, we see that the minimum size we need is 4 millimeters for the multi-layer insulation. We see blue curve is for the internal side of the F-TPS, and then for the multi-layer insulator, the green one, and we see that it's kept below 60 degrees at all time, 58.9 to be precise. And that's it. And now we follow this scheme to validate everything with the external time-varying temperature. So first, conduction through the F-TPS. Then we assume that the internal temperature of the F-TPS is the same as the external one of the multi-layer insulator, and then conduction through the multi-layer insulator. These are expression, and we get these profiles of temperatures, and with these thicknesses, we see that we comply with the requirements. In this case, we see that it's actually more demanding than the specifications, because also the data, the input data that we do, is just good for reference for validation, for to have this for validation, because it's taken from degrees, but we said that in degrees we're using an ideal, thermal ideal material. So I include some arbitrary margins of multiplying everything by 2. So the values are not reliable, but we see that the tendency is the same, and that we can also use this approach for a time-varying profile. Then we finally did a quick rough structural analysis of the heat shield. This F-TPS again, this cone because as this is the exposed surface during reentry, it will determine the drag coefficient and the ballistic coefficient with it. So the requirement is that the maximum deflection has to be less than 15 degrees. And for that, we're gonna model it as it was supported by 8 beams made of shape memory alloy material, and nickel in particular. And these beams are gonna be modeled in this first approach as slender beams in fixed cantilever condition, and with a circular cross section, whose diameter D is the parameter we want to size. And in particular, it would have an effect in the second moment of inertia that is going to appear in the analytical expression. So this is the applied load, which is based on the surface pressure defined from e.NOVA's specifications, 3,400 pascals. This is going to be uniformly distributed along all the surface of the cone. And then from this total force, we divide it into the 8 beams. And then for each beam, we distribute it uniformly for the length. And so this is the value of the load and the distributed load for the beams. And the requirement is that the maximum displacement has to be that of a maximum inclination of 15 degrees, so from 60 to 45 degrees. And we get that the maximum deflection is 78 millimeters in the tip. This is a simple problem with analytical expression from the Euler-Bernoulli's equation. For the fixed cantilever beams, this is the expression that depends on the length of the beam, and especially on the moment of inertia, where the diameter is implicit. And again, we iterate, and we get that for 6.5 millimeters of thickness, we get a tip displacement of 74 millimeters, which is less than the 78 that we required. And this is good because the mass of the beam would be only 64 grams. For the 80 beams, it would be around half of a kilo. This is good for the tight mass budget of the system. And here we can see that it's possible that we should introduce some margins to take into account the model uncertainties, because it's a preliminary and rough model, but we have to take care here because variance is very sensitive to the variations in the diameter. If we multiply by 2 the diameter, the mass is increased by 4. So it's something to take into account. So in conclusion, to recap a bit all what was done during the project, we first done this Trectory definition methodology that was implemented in MATLAB, and it's easy to iterate for different cases. We studied the landing accuracy, where we found that the ballistic coefficient is a major driver, together with the altitude of the perigee and the argument of the perigee. We gave some analytical expressions for this first approach, and we saw also the effect of these parameters on the accuracy that we have to request to the other subsystems, like the propulsion and AOCS systems. During the second semester, we also selected a propulsion module among different candidates. We defined some requirements and selected 8 possible candidates for 1U propulsion modules. And then we also defined a payload module for this in-orbit demonstration validation mission, setting the preliminary requirements and designing an architecture and proposing some hardware solutions to fulfill them. Then we focus on the thermal system, and this is important that all the methodology presented was implemented in a simple Excel sheet that was shared with e.NOVA, so that they can now easily iterate with the parameters and play with different geometries and materials and get the sizing. With this, we could size the F-TPS and the MLI for the payload, and we validate this with different input temperatures. And same for the heat shield, the structural analysis, we implemented it in an Excel sheet, so it can also be easily iterated for different properties of the parameters, loads, etc., number of beams, and so. And for that, we can size the thickness and the mass of the beams. So working perspectives of the BFS project from now on for e.NOVA is basically to go further in all this analysis. So to validate the data of the landing accuracy, ideally would be with this in-orbit demonstration flight. Also have to confirm the propulsion module, so consulting the suppliers and doing a final assessment with taking into account the cost as well. For the materials, it is targeted to validate these materials and also this analysis with a test in a plasma wind tunnel in DLR in Germany. And finally, they are working on the application for the Plan de Relance from CNES to get some funding from the project, and for that there's advanced contacts with platform, payload, and launch suppliers. Finally, last but not least, they got an abstract accepted for the FAR 2022 conference in Germany by ISA, and we will work on the paper to be submitted by the 1st of June, and then there will be an oral conference, conference there. So that's all. Thank you, and let me know if you have any questions or if I've